Greetings and salutations, magical chemists. Today we get to learn about reaction mechanisms, which explain the exact series of steps in which a reaction actually occurs. For example, if you have the overall reaction where there are two nitrogen dioxides reacting with one fluorine gas particle to form two NO2F compounds, the actual reaction mechanism can be broken down into two steps. First, one of the nitrogen dioxides reacts with one of the fluorine gases, forming one particle, and then in the second step, nitrogen dioxide will react with the single F that was created as an intermediate. So the idea is that when you're looking at the individual steps of a reaction mechanism, you're actually looking at what is happening step by step, beginning to end, and how this chemical reaction is actually happening. Each one of these steps is known as an elementary step. These steps cannot be broken down into anything simpler. They're as simple as it gets. So they actually are happening exactly as written. So they represent the chemical species that are directly interacting. You might have noticed that there was a particle in this reaction mechanism that doesn't show up in the overall reaction. So F, just all by itself fluorine, not diatomic, crazy but true, is produced and then it's consumed. So notice, it will cancel out if we add the two steps together to get our overall reaction, but it still exists. So this is what's called an intermediate. Now, as I mentioned, when you add up the overall steps together, just like in Hess's law when you're adding reactions, so when you add them together, they must add up to be the overall balanced reaction. There's some terminology that comes up when you're talking about elementary steps. Specifically, it's called molecularity, which is an awesome word. Molecularity is a fancy way of talking about the number of molecules that are actually participating in a given elementary step. So if you have a unimolecular elementary step, well, uni means one. There's only one reactant particle involved. It could be decomposing or it could be reacting with a solvent, but basically only one reactant particle exists in that step. A bimolecular reaction, well, bi, of course, means two. So a bimolecular elementary step is when two reactant particles are involved. And then a termolecular reaction would be an elementary step with three reactant particles. It is very important to recognize that termolecular elementary steps are very, very rare. Because according to collision theory, if you had a termolecular elementary reaction, you would have three reactant particles that would have to simultaneously collide with the correct orientation and sufficient energy, and that just almost never happens. So you are expected to know on an AP test, if someone says, hey, I think that this might be a termolecular elementary step, should that be true? You're expected to be able to go, no, that's not going to happen. That's super rare. Okay, so speaking of elementary steps, it turns out there is something very advantageous about them. You may have been wondering all this time. You know, of course, that the rate law for the overall reaction is determined experimentally. But you may still be wondering, but why? Why are these reaction orders? Why is it first? Why is it second order? Well, the elementary steps explain it. Because, every elementary step in the mechanism has its own activation energy and its own rate law. And now, of course, the rate law and the orders for reaction must be determined experimentally. The shocking part is that the rate laws and orders of an elementary step can actually be derived from the stoichiometry of that elementary step. What? So let's look back at that example reaction again. Of course, we got our nitrogen dioxide and our fluorine gas. So when you're writing the rate law for the overall reaction, the order with respect to NO2 and the order with respect to fluorine gas come from experimental data. But if you are looking at an individual reaction mechanism for each step, notice I can write the rate law for each step, and when I look at my coefficients, they become the exponents. So notice NO2 and F2 both had a coefficient of 1, it's implied, so that means they were both first order with respect to both nitrogen dioxide and fluorine gas in the rate law for step 1. And then it turns out in the second step, well, they were actually also both stoichiometric coefficients of 1. So in this case, the rate law for the second step, again, is showing first order for both of the reactants. But you're actually getting these numbers from the coefficients. But this only works for elementary steps. Do not try it for the overall reaction. So let's look at a beautiful chart that I stole from the textbook that summarizes this delightfully. So you can determine, so if you're given an elementary step, if you have only a single reactant particle, then it has a molecularity of 1. It is unimolecular. But if you have 2 of the reactant particle A, notice we would normally write that as 2A. Well, now, of course, this is bimolecular, and it had a stoichiometric coefficient of 2, so that means for that elementary step, it is second order with respect to A, whereas when it was unimolecular, it was only first order with respect to A. Craziness! And of course, it just keeps going in that direction. So of course, molecularity of 1 is unimolecular, molecularity of 2 is bimolecular, and the molecularity of 3 is termolecular. Okay, so now we know how to write the rate law of the individual steps. Let's see how we can use the rate laws from the individual steps to actually go ahead and predict the experimentally determined rate law, because yes, it can totally be done. To do so, we need to look at something known as the rate determining step, or the RDS. This is what's known as the slowest elementary step. So the idea is, if you have a reaction mechanism in multiple steps, the product cannot be produced any faster than the slowest step out of all of them. So the slowest step determines the rate of the overall reaction. It's important to note that the slowest step, aka the rate determining step, or RDS, it is the slowest because it has the largest activation energy. Okay, so if you want to go ahead and determine the rate of the overall reaction, and of course you do, you have to combine the rates of all of the elementary steps up to and including the rate determining step. Now notice in the diagram below, you can draw an energy diagram for a 2 or 3 or 5 or 7 step mechanism. Every single step is going to have a bump, an activation energy, but whichever one is the highest, well, in this case, the first bump is the highest, that means that this one must be the rate limiting step. So step 1 is the RDS in this particular reaction mechanism because it takes the greatest energy to overcome, or the greatest energy basically to overcome that transition state. So there are going to be 2 transition states in this mechanism, but the first one is the highest energy. Okay, so let's talk about how you would need, if you were given a reaction mechanism, how do you know if it's a valid reaction mechanism or not? Well, there are 2 conditions that you have to meet. First, when you add up the elementary steps, it's got to add up to the overall reaction. Secondly, the rate law that's predicted by the mechanism has to be consistent with the experimentally observed rate law. These are very common free response questions, and so it's important to recognize that you have to be very specific if you want to get credit for your free response, and I know you do. The trick is, if you want to relate the rate law that you derive from the mechanism to the experimentally determined one, you have to talk about the coefficients from the rate determining step and compare that to the exponents on the rate law. Now remember, the exponents on the rate law, that's the order with respect to each of the reactants. Okay, let's go ahead and try a practice problem so you can see what this actually looks like. Okay, so here is a given reaction mechanism. It is 2 steps, and the first step is the slow step, the rate determining step. First, if I want to find the overall reaction, I just have to add them up. And yes, if this is a free response problem, you have to show the adding. Yum. Okay, when I take my 2 elementary steps and I want to add them together, first we see if there's anything that can cancel. Well, notice in this case, A2 is an intermediate. It's produced in the first step and consumed in the second, and thus it is dead to us. Well, that was the only thing we can cross out. So that means both of the other reactants are going to be part of our overall reaction. And then there's only one product left. So that product has to be the product of our overall reaction. Okay, part 2 says, predict the rate law for the overall reaction and justify. Okay, first, before we do that, let's go ahead and look at the rate law for each of the steps in the reaction mechanism. Now, the rate law always follows the same format, right? It's rate equals decay. What we do to differentiate between the rate constant K for each elementary step is we call it K1 for the first step and K2 for the second step. All right, take a moment, and I would like you to fill in what each one of these would be with respect to the reactants of that given step. And when you're ready to check your answer, of course, unpause the video. Okay, how did you do? Did you see that the stoichiometric coefficient of 2 meant that this very first step is second order with respect to A? But for the second step, stoichiometric coefficient of 1 meant it was first order with respect to A2 and B. All right, well, this was important because remember that I need to look at to predict the rate law for the overall reaction, I need to look at the rate law of all the steps up to the rate determining step. Well, the rate determining step is the slow step. So, hey, that makes our lives easy. The first step is the slow step. That means, no, don't even need that one, because this one must be the rate of the overall reaction, at least as predicted from this reaction mechanism. So according to this reaction mechanism, we would predict that this reaction is second order with respect to A. So let's see how we could justify this. First, we have to specify which one was the rate determining step, or the slow step. That means the rate law actually can be determined by the stoichiometry. Well, since A has a coefficient of 2 in the slow step, the reaction must be second order with respect to A. And of course, B, which is one of our reactants, doesn't even show up in the slow step. So that's why it's 0th order with respect to B. So I know that was kind of a long thing to write, but the important part is talking about the coefficients. Remember, A has a coefficient of 2 in the slow step, so that's why it's second order with respect to A. B doesn't exist, so it's 0th order with respect to B. Okay, from part C, it says identify the intermediate and justify your reaction. Your answer. Well, I might have already mentioned this when we were summing it up, but if you don't remember, you should try this anyway. And when you're ready to check, well, unpause the video. In this particular reaction, A2 is an intermediate. Now, the way you have to justify that is you have to talk about the idea that it's formed or it's produced in an early step and consumed in a later step, because that's what makes it an intermediate. All right, so that's the basic idea for the kind of questions you could be asked when you're talking about a reaction mechanism and identifying the rate law and looking at intermediates and stuff like that. So let's try one more practice problem and then you shall be free. Well, till the next video, of course. Okay, so here is a given reaction and a suggested mechanism. So the first thing you're going to do is you're going to label each step of the reaction with its molecularity. Then they tell you, okay, here's the experimentally determined rate law. Well, if that's the experimentally determined rate law, which of the two steps must be the slow step? I would like you to try this on your own first. 1, because it's fun. 2, delicious chemistry. But 3, it's good practice. And then when you are ready to check your answer, unpause the video. All right, make sure you've tried it on your own, and then we can go over the answers. Okay, so for part A, hopefully you can see both of these steps are bimolecular because there are 2 reactant particles in each step. Part B was way more fun because this one you had to really think about. Well, okay, notice they are giving you an experimentally determined rate order that is first order with respect to NO2 and first order with respect to F2. Well, hey, did you recognize that is exactly matching the stoichiometric coefficients of the very first step? If you did, Merry Christmas, you win, because number 1 must be the slow step. And of course, our reasoning again focuses on the coefficients. As we noted, both NO2 and F2 have a coefficient of 1 in step 1, and that is consistent with the given rate law, which is first order with respect to both NO2 and F2. Ta-da! And there you go. All right, so now you have mastered the glories of reaction mechanisms. Okay, technically, there's one thing we haven't learned yet, but we're going to learn in next class, what to do if the slow step is the first step. So we're going to look at that in next class. But you are ready to move on to the next video. Catalysts. Let's speed up our reaction rate. It'll be amazing. I'll see you there.